if we want to characterize the flow here, we need to often use something called the hydraulic diameter. So if you have some profile as a circle, right, and I want to characterize the boundary layer in terms of some characteristic length, it would make sense if you have like an infinite or two plates that have sort of infinite width. Obviously, you could take half of the thickness between those plates or half the gap. If you have a circle like this, you just look at the radius, right? That's going to be where the boundary layers are going to meet. If you have a shape like this, where it's maybe not obvious, we can still express correlations generally for shapes even that are sort of odd if we use the hydraulic diameter. So the definition for that is usually d sub h, hydraulic diameter, is equal to 4 times the cross-sectional area over the perimeter. So I could take, I take these two shapes for example, and just see how it comes out, which is fairly obvious. But for a circle, it would be, so dh is equal to 4 ac over perimeter, which is, for a circle, 4 pi d squared over 4 times the perimeter, which is pi times d. So that just gives us d. It makes sense. So our hydraulic diameter for a circle is the diameter. Uninteresting. For a rectangle, it would be dh is equal to 4 times a times b. That's our cross-sectional area that's available for flow, divided by the perimeter, which would be 2a plus b. That's just your general formula. OK, so hydraulic diameter. If we want to then, let's see. If we want to compute the hydrodynamic entry length, so it's usually important for us to figure out, OK, we have this shape, we know the geometry, we characterize it in terms of the hydraulic diameter. The next thing we'd want to do is figure out, is the entrance length important to our problem, like I said. So you want to maybe compute that length, that xfdh, and we can do that using kind of the growth models that we have from our previous discussions. So let's see, to use a growth model there, we would say delta m, let's say we're treating laminar flow here, so laminar is approximately equal to, it was 2 times the kinematic viscosity nu times time. That was our growth model, just approximately. So applying that to a steady problem with flow, that becomes 2 square root of nu times x over um. That's our mean velocity here. Just be careful when we're doing this. We're talking about an internal flow. You always want to reference the mean condition, right? And the same thing will go for temperature, by the way. We'll stop using T infinity. It becomes the bulk mean temperature. OK, so anyways, that's our growth model there. Let's keep moving. So what we want to do is figure out this entry length. So let's say, using this model, and noting that our boundary layer growth is about dh over 2. You'd say dh over 2. That's about our delta m laminar. That equals the right-hand side. So that's approximately then 2 square root of nu times, so we want to look for xfdh over u sub m, right? We're trying to solve for xfdh there. So solving for that, we would get, let's see, dh squared over 4 is approximately equal to 4 times mu times xfdh over rho u infinity. So we're just squaring both sides. And then substituting the definition of viscosity in there. So then we solve, we get, let's see, xfdh over d sub h is approximately equal to 1/16 times rho u sub m dh over mu. OK, rewriting that very slightly, it becomes XFDH is equal to 1/16 is 0.063 approximately. Reynolds number in terms of DH times DH. Hopefully that makes sense. So 0.063 is 1/16. Reynolds number is this here, right? This is our Reynolds number. And then DH we just bring over from this side. OK, so with this now I'm able to compute or approximate where I think this thing is going to become fully developed. So again, the steps for internal flow would be find the geometry, DH, figure out is the entry length important to my problem using this calculation. And then if it is, you can adjust your correlation appropriately. OK, so let's see. So we have that model. I guess another question is we've assumed this flow is laminar, right? The growth model that we assumed here is laminar. What happens when it becomes turbulent? And I guess when does it become turbulent? So let's look at a way to estimate when it will become turbulent for this type of flow. So again, remember kind of back to the concepts here. Here's our laminar condition. We have velocity coming in. We have it eventually becomes fully developed. That growth is proportional to the square root of x. So when you get to a turbulent condition, that growth really takes off. Like you have this nice laminar development. Once you transition to turbulence, that remember the diffusivity associated with turbulence is much higher. So that layer is going to grow basically immediately to merge together. Right? So you have this slow growth region and then fast growth region. So we need to just be able to estimate kind of where that transition point occurs to get a sense of when the boundary layers are going to meet. So that's what we call the x critical value. So we've labeled here, that's the transition point from laminar to turbulence. So we would estimate that. Let's write out our equations from the last slide. So we said x FD H. And let me just specify this is x FDH laminar. So that's the point at which the laminar boundary layers would become merged. So divided by DH is equal to 0.063 times Reynolds in terms of DH. And then, let's see, for this we want to use the idea that Reynolds critical, or transition from laminar to turbulence, is equal to rho times u infinity times x critical over mu. Or solving for this in terms of x critical, we get x crit is equal to Reynolds critical times mu over rho u infinity. And then based on this, we're going to be able to solve out to figure out what that x critical is. So before we move on, I'm going to ask some questions on Top Hat, and we'll just kind of think about the way to frame this kind of stuff. So we have a transition that's happening. We want to be able to estimate kind of when this transition is happening relative to the merging of the boundary layers. So I have a couple questions to ask there. OK, so the question is, an internal flow that's become hydrodynamically fully developed will transition to turbulence, A, soon after, B, a significant distance after, C, once the flow becomes thermally fully developed, or D, never. So remember, XFD is the distance at which flow becomes fully developed. OK, so let's see the responses. OK, so half of you say it will never transition to turbulence. Some say soon after, significant distance after. One or two say once the flow. So the right answer is never. So why is that? An internal flow that's become hydrodynamically fully developed will never transition to turbulence because remember, what is it that's causing the transition to happen? It's a change, it's a continued change in the ratio of momentum forces to shear forces. Once you have a fully developed flow, it stops changing. So there's nothing that's going to cause it to become turbulent. All right. So one caveat to that is if you have a flow where you have, say, a significant pressure loss as a function of distance, it's a function of flow length through the pipe, and the properties of the fluid are changing as you continue to go, even though it's fully developed. At some point, the properties might change to a point where you develop turbulent flow. But in a steady property condition, it would never transition. All right, let's go one more question here. Once internal flow transitions to turbulence, the viscous sublayer thickness, right, remember the viscous sublayer is the little layer that forms in turbulent flow. So that will grow a small amount indefinitely, grow until the flow becomes fully developed, or remain constant after the transition region. Missing one? Okay. All right, let's see the responses here. All right, so we're pretty split between grow until the flow becomes fully developed and remain constant. So first of all, it will not continue to grow indefinitely because once you're fully developed, the turbulent boundary layer is going to meet at the middle, and even the forces in the turbulence wake region, those are kind of staying constant relative to the viscous sublayer. So there's not this, there's sort of nothing that's changing after you have become fully developed. So let's see in terms of which of these it is. Okay, so the answer is B. I guess there's a subtle difference here, right? So if I'm in the transition region, let's say you sort of start off transitioning to turbulence, that viscous sublayer is going to start forming. It's going to establish itself, and then it's going to continue to grow, right? As if it was external flow, until the point where the boundary layers meet. So the key point here is things will look like external flow until the boundary layers meet, even if it's a short distance, right? It will continue to look like external flow until it meets. So this is the one I was going for. Questions on those? Yeah, I guess the assumption here is that we're talking about time averaged conditions. So on a time average basis, at any position, you will not see growth. But if it was, yeah, like if you look at really detailed, really short time steps, there's going to be an eddy that comes down and sort of swoops away part of the viscous sublayer, but it will reestablish itself, right? So the thing, and I guess one of the important points about viscous sublayer versus the wake region or the eddy region is that when the eddy sort of is interacting with the viscous sublayer, there's all this momentum that's coming down, right? And that momentum, it has to be counteracted by the shear stress in the fluid. So at any moment, you might get these little fluctuations. But the reason why the viscous sublayer is the thickness that it is because that's sort of the limit at which the shear in the fluid can withstand the momentum that's coming in from the turbulence. Okay, so where are we? So we're back here. From that, I guess we learned that if XFDH laminar is less than X critical, then the flow will always be laminar.